Come, now let's look at a couple of more interesting examples of vector spaces. So, number 8, yeah. What if I take the set of all functions on some interval 0 to L, let's say. So, along the real line, let's say between 0 and L, I'll take any function, the set of all functions between these 2 points. Do these form a vector space? So if I take one function f and if I take some other function g and if I add them up, is this also a function? Yes, this is also a function on 0, L. If I take any function f and I multiply it by a scalar number, so if this is f, then a times f will just scale it by a certain factor. So that is also a vector. That's also a function defined on 0, L. So it belongs to the space. Is there a null vector? Yes, and that null vector is just this function which is 0. Because if I add the 0 function to any function, I'll just get that function back. Is there an additive inverse? Yes, there is. Because for every function f, there is a function minus f, which might look something like this, such that f plus minus f gives you 0. So yes, this set of all functions on 0, L is a vector space. What if I take the set of all functions on 0, L with the condition that the value of the function at 0 has to be some p, let's say. So all functions, let's say this is p. All functions which start from this point. So this function, all of these, do they form a vector space? Clearly no, for multiple reasons. If you take one vector starting over here and another vector starting over here, so one function starting at p and another function also starting at p, you add them up, you're going to get a function that starts at 2p. So that doesn't belong to the set. Another way of saying it is that the null vector cannot belong to this because the null vector is a 0 function and its value is not p at 0. So this is not a vector space. What if I take the set of all solutions of the simple harmonic oscillator differential equation? This is a very interesting example. So if I take, you know what the differential equation is for the simple harmonic oscillator. So all solutions of this equation, do they form a vector space? And the answer is yes, they do. Because you will notice, let's say if f is a solution of this differential equation and if g is also a solution of this differential equation, then f plus g is also a solution. You can verify that. So I'm going to use the dot notation because it's easier. So if f double dot plus omega square f is 0 and g double dot plus omega square g is 0, then you can check that if you just add them up, f plus g whole double dot plus omega square f plus g is also 0. And similarly, if you do scalar multiplication with some a, then af the whole double dot plus omega square af is also 0. Why does this work? Because the derivative is a linear operator. So derivative of f plus g is derivative of f plus derivative of g. Derivative of a times f, a is just a scalar number, so you can pull it out of the derivative. So it just becomes a times derivative of f. So because of that, these conditions are satisfied. 0 is obviously a solution to the simple harmonic oscillator. That's the case in which there is no oscillation happening. Just x of t is 0. So the null vector belongs to this set. The negative of any function, of any solution, is also going to be a solution. So all solutions of the simple harmonic oscillator also form a vector space. So for example, sine omega t, cosine omega t are solutions. Then sine omega t plus cosine omega t will also be a solution. So these are some nice examples of vector spaces. Okay, the next concept I want to introduce is that of linear independence. Li. Linear independence is basically just saying that given some set of vectors, and let me call them v1, v2, vn. Question is it possible to write any one of them in terms of all of the others, as a sum of all of the others? Can we write, let's say, vn as some linear sum or linear combination of all of the other ones? So a1 times v1 plus a2 times v2 and so on. If I can write this, then we say that they are dependent on each other, or they are not linearly independent. These vectors are not linearly independent. So I'll give you a very simple example. Suppose I take three vectors. v1 is I hat. So I'm looking at the usual vectors that we talk about in R3. And if I take the vector v2 as j hat, and if I take the vector v3 as 2i minus 3j, then this set of vectors is obviously not linearly independent, because it is possible to write one of them in terms of the others. So I can write v3 as being the scalar 2 times v1 plus the scalar minus 3 times v2. So therefore, not linearly independent. Let's take one more example. Suppose I take the vector v1 as I minus 2j, and if I take the vector v2 as 2i minus 4j, then you can see that v2 is just the scalar 2 times the vector v1. So I can write one of them in terms of the other. Of course, I could also have said v1 is half times v2. That's also perfectly fine. Point is, you can write one of them in terms of the other ones. Therefore, this set of vectors is also not linearly independent. What if I took v1 as being I plus j and v2 as being I minus j? Think about it and convince yourself that there is no way that you can write I minus j in terms of I plus j, or I plus j in terms of I minus j. Therefore, this set of two vectors is linearly independent. Okay. So question is there like some nice general way of seeing when vectors are linearly independent or when they are not linearly independent? What if we look at I and j and k? Are these linearly independent? Yes, because you cannot write any one of them in terms of the others. So linearly independent. What if I take I plus j and I plus j plus k? Yes, these are also linearly independent, because it is not possible to write, let's say, I plus j plus k purely as some linear combination of I and I plus j. Or the other way around, it is not possible to write I as some linear combination of I plus j and I plus j plus k. Try it out. Try and find various combinations. You will find that it's never possible to do it. Therefore, these are also linearly independent. Okay. So how to check in general whether a set of vectors is Li or not? So the way to do it is as follows. You see that if the equation a1 v1 plus a2 v2 plus an vn, if the sum of these vectors is 0, this is an equation. If this equation implies that all these scalars ai have to be 0, or rather, if this equation can be satisfied only if all these are 0, then the vectors are linearly independent. How do we justify saying it? Suppose this equation could be satisfied with one of these coefficients non-zero. So this is a proof by contradiction. Suppose a3 was not 0. Then what we could have done is we could have written v3 in terms of all the others. I could have said that v3, I'll just take all the other vectors on that side. So I'll get 0 minus a1 v1 minus a2 v2 not v3 minus a4 v4 all the way till an vn divided by a3. Right? Because a3 is non-zero, I can do this. So what I have proved is that you can write v3 in terms of all of the other vectors. Therefore, not Li. So the only way for a set to be linearly independent is if you cannot do this, which means all of those coefficients have to be 0. So if I give you an example now, and I say show that these vectors 1 1 0 1 0 1 and 3 2 1 are not Li. So the way to do it would be you set up an equation like that. So this is like your v1, this is v2, this is v3. So you set up an equation like this: a1 v1 plus a2 v2 plus a3 v3 is 0, and you solve for a1 a2 a3. If you find that this equation requires a1 a2 a3 all of them to be 0, then the set is Li. if you get some non-zero values of a1, a2, a3, then the set is not Li. So over here we will get something like a1 times 1, 1, 0 plus a2 times 1, 0, 1 plus a3 times 3, 2, 1 is 0, 0, 0. So from this you get three equations. What do you get? a1 plus a2 plus 3, a3 is 0. a1 plus 0, a2 plus 2, a3 is 0. And 0 times a1 plus a2 plus a3 is 0. So you solve these simultaneously. I will just write down the answer from my book. Turns out that the solution to these is a1 equal to 2, a2 equal to 1, a3 equal to minus 1. So clearly this equation can be satisfied for some non-zero values of a1, a2, a3. Or in other words, you can write a3, you can write v3, this 3, 2, 1. How? So what we have got is 2 times 1, 1, 0 plus 1 times 1, 0, 1 minus 1 times 3, 2, 1 is 0, 0, 0. So that means you can write 3, 2, 1 in terms of the others, no? 3, 2, 1 is just 2 times 1, 1, 0 plus 1 times 1, 0, 1. So you can write one of them in terms of the others, therefore not Li. If we had got instead a system of three equations which could only be satisfied if a1, a2, a3 was 0, we would have said, yeah, sure, this is a linearly independent set because you cannot write any of the vectors in terms of the others. Now, the concept of linear independence is important because it allows us to define what is called the dimension of a vector space. So we say that a vector space V has dimension n. We say it's an n-dimensional space if it can accommodate a maximum of n linearly independent vectors. Let's see what the statement means. Suppose I'm talking about R2. So in R2, which is just your two-dimensional space, let me take two vectors which are linearly independent. So let me take a vector v1, which is I hat, and let me take a vector v2, which is j hat. And you will notice that if I take any other vector, I can write it in terms of v1 and v2 because I can write it in terms of I hat and j hat. So any other vector that I take v3 in R2, I will be able to write it as something times v1 plus something times v2. There is no way that I can get a third vector which is going to be linearly independent with v1 and v2. It will depend on v1 and v2. So maximum, that means I can have two linearly independent vectors in this space. Therefore, we say that R2 is a two-dimensional space. One thing I want to make clear, this choice of v1, v2 is not unique. I could have taken any two vectors. I can take my v1 like this and I can take my v2 like this. And I want you to convince yourself that even in this case, any third vector I am able to write in terms of v1 and v2, because I can always multiply v1 by I can always multiply v1 by some scalar, I can multiply v2 by some scalar, and I can then add them up to get any other v3. There is a theorem which says that in an n-dimensional vector space, any vector v can be written as a linear combination of n linearly independent vectors. And I mean, the way to argue this out is that suppose if this was not true, if there was some vector v which you could not write as a linear combination of n linearly independent vectors, that means this vector is linearly independent with all of those. That means total there are not n but n plus 1 linearly independent vectors. But that's not possible because we've said this is an n-dimensional vector space, which means maximum it can have only n linearly independent vectors. Therefore, it must be possible to write that vector v in terms of these n Li vectors. So this brings us to the next important concept, probably the most important concept when you're doing quantum mechanics, and this is the concept of a basis. So in an n-dimensional vector space, V, any set of n linearly independent vectors is called a basis. And then as per that previous theorem that we saw, it is possible to express any vector in V in terms of the, or as a sum or a linear combination of a set of n Li vectors it's possible to express any vector in V as a linear combination of the basis vectors. Or another statement that is used, we say that the basis vectors span the entire vector space. All of these statements just mean that any vector you can express in terms of these certain vectors that you've designated as the basis vectors. These are a set of n linearly independent vectors. So for example, again, don't get very alarmed by the language and the new words that I introduced. Just think of it in terms of the vectors that you're already familiar with. So for example, in the vector space R3, three-dimensional space, I can choose my basis vectors to be I, J, K. R3 is a three-dimensional space because there are maximum 3 linearly independent vectors. And I can choose these 3 linearly independent vectors as I, J, K. And then any other vector in R3 I can write in terms of I, J, K. I minus 5J plus 7K. That is a linear combination of these basis vectors. These basis vectors span the entire vector space. That means starting from ijk, I can write any vector in the vector space. That is what this spanning means. Okay, so it's quite straightforward. It's a set of vectors in terms of which any other vector you can write down. Let's take one more example. We were talking about the set of all 2 cross 2 matrices, right, earlier. So set of all 2 cross 2 matrices. For this, I can write the following basis set: 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. Tell me, do you think this makes sense as a basis set? Because then any 2 cross 2 matrix, which is of the form A, B, C, D, I can write as a linear combination of these. I can say it is A times 1 0 0 0 plus B times 0 1 0 0 plus C times 0 0 1 0 plus D times 0 0 0 1. So again, these 4 vectors, which I have chosen as my basis vectors, these ones, span the set of all 2 cross 2 matrices, or they form a basis of the set of all 2 cross 2 matrices. Or it is possible to write any 2 cross 2 matrix as some linear combination of these 4 basis vectors. These numbers in the combination A, B, C, D, or for example in the R3 example, I could have said that I have a vector which is 2i plus 3j minus 5k. These numbers over here, 2, 3, minus 5, these are called the components of this vector. Components of the vector with respect to this basis. And this is a very important statement. This is something that you should remember. The components of a vector depend on what basis I have chosen to define them in. If I change the basis vectors, there's nothing unique about a basis. So again, it's nice to take examples and look at this. Let's look at R3 because we are familiar with it. I can choose let's make an even simpler case. Let's choose R2. R2 is just a 2-dimensional plane. So normally, and let's take this vector. Okay, this is the vector V of interest. Again I've cut myself off. So I can choose any number of bases. So if I choose for the basis, if I take a basis V1 as I and V2 as J, so that means this is my V1 and this is my V2. Then I can write, I can write V as 1 times V1 plus 1 times V2. So I will say that in the basis I comma j, the components are 1 and 1. But I can instead choose a different basis. What if I chose these two as my basis? So let me call this w1 and w2. Now in this basis, my vector v is given by minus 1 times w1 plus minus 1 times w2. So now my components are minus 1 comma minus 1. Okay, I don't have to take these two. I can take this x1 and some other thing, and this as x2. Now in this basis, I can write my vector v as just x1 and no contribution from x2. So now my components in this basis are 1 comma 0. So in general, any two linearly independent vectors I can pick as my basis, and then depending on what basis I have chosen, the components of my vector will change. Note that the vector has remained the same. It is still that vector v given by that white arrow which I am trying to describe. So the vector remains the same physically. So if you were thinking of it in terms of the velocity of some system, or the acceleration of some particle, or the electric field generated by some charges, that the physical reality of what is the velocity of the system, what is the acceleration of the particle, what is the electric field, that remains the same. That doesn't depend on what basis you have chosen. But the components, as you describe it, depend on what is the basis that you have chosen. So you choose a basis and you stick with it. For each basis, the components are going to be different. So in general, for basis vectors v1, v2 and so on, I can write my vector v as some linear combination, sum of these components ai times these basis vectors vi. a1 v1 plus a2 v2 plus a3 v3 and so on. And these are the basis vectors, these are the components.